In this video, I'm going to show you how to use a graph given to you to solve an application problem. And so I have a little bit of context here, and not only that, but I have context given to me in my graph as well. So I'll read the scenario and we'll talk about the application problems for this linear equation. It says the graph below shows the relationship between the number of hours that Josh spent driving and the number of miles Josh is away from his house. So number of miles from his home starts at 160, and then as you see over time, he's getting closer and closer and closer until he is no miles from his home, and that took him 4 hours to do. Now it's easy to just say, oh, well, my slope is down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. Well, you're partially true, but you really have to look at your scale. And that's a big mistake that some people make by not interpreting the graph right because they don't look at the scale. Our scale here does not go down 2, it's really going down many more miles than 2 miles. So I just want to note that in your graph, it's super important to note that this scale is not going by ones. So it is not correct to say down 2 over 1. In fact, it would be down from 160 to 120. That's a difference of 40 miles in 1 hour. So 40 miles in 1 hour, and then another 40 miles in 1 hour, and then another 40 miles in 1 hour, and then from 40 to 0, another 40 miles in that hour span. So double check your scale so you don't interpret your slope incorrectly. Well, my first question here says write an equation in slope-intercept form. Well, lucky for us, we actually already started looking at the slope of our graph by looking at how it's going down. And then our intercept we'll just find by looking at the graph our starting value on the y-axis. So if my slope-intercept form is y equal to mx plus b, I'm actually already on my way to filling that in. It would be y is equal to, now my slope, we went 40 miles closer to home, plus we started at, because look at the graph is going down, so I know that needs to be negative, right? We're getting closer to home. And then we started with 160 miles to go. Be sure to define my variables. Well, this is going to be even easier because I have my variable labeled on my x-axis, so I'll record that, and my variable recorded on my y-axis. So I'm going to say let x represent time in hours, and then let y represent number of miles from Josh's home. Then letter B, write an equation in standard form. So I have slope-intercept form here, but now standard form to represent the linear relationship. Define our variables. I can just copy this down, or if it says define my variables, you know what I'm going to do? I'm going to do a quick cheat and say I did here. So standard form, let's talk about that. Ax plus by equal to c. Now in this equation, standard form, you're supposed to have a be positive and no fractions allowed. So no fractions at all. And as I'm looking at this, I'm pretty good because I don't have any fractions here, and I just need to figure out how to get my x term and my y term together on the same side. So I need to move this x term over to this side to join with the y. So if I have y is equal to negative 40x plus 160, and I want to get it to this form, I'm going to add 40x. So I'm just kind of doing my work here off to the side. My y and my x terms are not alike. They do not have the same letter, so they need to stay separated by that plus sign. I have a 40x and I have a y term there. They have to stay separated because they're not alike. They're not like terms with the same letters. And now my 160 is alone. So my standard form is a 40x plus 1y equals 160. Then it says, for letter C, interpret my slope. And I actually have some of that written down up here. As we were looking at how our equation was going down, we actually did define our slope here. So I'm going to copy down for here. We had negative 40 And this represents traveling 40 miles per hour to get closer to home. And then identify my x-intercept. I'm going to do that. Now this equation here, standard form, is incredibly useful for finding our x and y intercepts. And if I want an x-intercept, I want to find the value for x when y is equal to 0. And that cover-up method is incredibly useful. So if 40x plus 1y was set equal to 160, if I put a 0 in here for the number y, letter y, then that means 40x will equal 160. If 40x is equal to 160, what's 1x? Well, let me get out my calculator here. 160 divided by that coefficient of 40 is going to be the number 4. So x is equal to 4. What does this mean? When x equals 4, y equals 0. Or, looking at my graph, when x equals 4, or when time is at 4 hours, my number of miles from home, the y value is 0. So I'm going to write a sentence, but just now put in the context of what we said x and y represent. And we actually did that here too. When x represents number of hours, so in 4 hours, the y, 0, represents number of miles from home. So in 4 hours, Josh reaches his home. And then identify and interpret my y-intercept. We actually know the y-intercept because of our slope-intercept form here. Our y-intercept was at 160, but also by looking at the graph, 160 is where we started on the y-axis, which is the point. 0, 160. Now again, our points are x, y. And if I just make a sentence now with my x representing number of time in hours, so 0 hours have passed, I know the number of miles away Josh is from his home. So he's 160 miles from home. So here, in 0 hours of travel, right before he starts, he is 160 miles from home. Great job today.